Good afternoon, everyone. Today I'd like to introduce you to Yuri Rzhanov, who is an associate research professor and senior research scientist here at CCOM. Yuri earned his PhD in physics and mathematics from the Russian Academy of Sciences and specializes in constructing large-scale mosaics from underwater imagery. Today he will be discussing how methods developed for computer vision can be used for inner pipe surface inspection.
Thank you. That's okay. Well, actually, I was thinking about tricking you into thinking that I just forgot to switch on the screensaver. But then I thought, you all know the title of the presentation anyway, so here it is. So, first of all, there are lots and lots of pipes around us. So, only in the USA, there are millions of miles of them. They transport all sorts of fluids and gases. And did you ever think about how many pipes there are in the house you live in? So that's the typical picture of a chemical factory. And there are so many factories like that everywhere in the world. That's another typical picture. This pipeline goes for thousands of miles across the steppes and all the other terrains carrying gas, oil, other stuff. And I'll tell you more. If you think there are lots of pipes inside us as well. So this is the network of pipes in the United States. But inside us, there are approximately 28 feet of intestines. And bloody hell, 60,000 miles. Yeah, that's impressive. But that all just to prove the point that my research is very, very relevant. So pipes require regular inspection. That's clear, right? Okay. Reasonable question. How this can be done? And the answer is clear as well. Of course, with pigs. Right? Pigs, crawlers, and cable systems. So what is pig? It's a pipe inspection. And these are huge things. You can see the guy over there. And they travel for thousands of miles checking for various cracks, usually using ultrasound and leakage of magnetic flux, and they are cleaning pipes as well.
Are these autonomous? How are they?
Yeah, they are. They are autonomous. They just travel and got in on one side and got out on the other side. But obviously they prefer straight pipelines or pipelines not bending very much. So what happens if the pipes have smaller diameter than these things? We use crawlers. So crawlers are wheeled machines, and they are using visual techniques to inspect the pipes. So in particular, this hardly see the pointer. Can you? Okay. So this beast is very, very clever. It's traveling along the pipe and doing that all the time. So it collects like 2-inch stripes and creating a mosaic from it. Without actually doing the mosaic, it just builds something which is easy to look at, easy to record, but again, this would fit only in that big a pipe. So what happens if we have even smaller pipes? And for that, we use the cable and camera solution. So at the end, there is a video head and a source of light. So light is illuminating the inside of the pipe. The video head is taking images. These images are transmitted to the top side because operator cannot fit into there. And the poor operator has to spend hours and hours watching live or recording this video, so this video can be watched at later on. It's not very convenient and it's very, very boring. So now, let's see what kind of data is available online and what kind of data we have to deal with in processing. So that's, by the way, awesome. Nice, huh? Yeah? And after that, they tell us that we don't do our job nicely.
That's not a pig. That's
No.
a rat.
No, that's why it doesn't clean the pipe. So the purpose of this research is using the existing or slightly modified equipment to develop some software solution of creating a continuous, sensible image of the inside of the pipe for monitoring, for visual inspection, and for saving for later, so it could be compared with inspections at a later date. So unfortunately, you can see from this image that it's not very good for our purposes. First of all, near range is well illuminated, but it's very small. Everything, almost everything, is covered with is dark because it's far away, and it's a far range, so the resolution is awful. And second, even more important reason is that this sort of footage almost never comes with the metadata, with the calibration parameters for the cameras, which is absolutely essential for computer vision solutions. So that's why I decided to go in this feasibility study along the proof of concept approach. It's a simulation. So first of all, I simulate images acquired inside the pipe. Then I mosaic the imagery, solve for the camera pose, which I don't know beforehand. Well, I pretend that I don't. And then I compare with the ground truth to see how well this works. So this is the setup that I was using. So I took the image, which is reasonably texture rich, which is very important for the for matching and creation of mosaics. And I build a pipe from these images. As image has finite dimensions in both dimensions, so I set some rules that this is this yellow column, and it ends up with the yellow column on another side, and so horizontally it just repeats every so often. So whenever I put my camera, my simulated camera, I get an image of something at least. So this is a typical simulated image. If I take the image near the main axis of the pipe, and it the camera looks almost along the pipe. That's what I see. And this is very similar to what you saw with the rat. It's except for non-modeled illumination conditions. So here I can actually see very, very far away. Otherwise it would be dark. It's almost useless. So the optimal conditions, from my point of view, is when the camera is near the side, one side of the pipe, and is looking almost normally to the opposite side. Then what happens, almost everything that camera sees is in the near range, is well illuminated, and it's easy to deal with. So this is the algorithm, and I don't expect you to read that. I promise I won't ever have the slide like that, but just a few points about it. So frames are corrected for lens correction, which is, of course, is not needed in the simulation case. Then the special points, special characteristic point features, which are called salient features, are extracted from 2 consecutive frames and then matched. So then on the basis of this matched, I construct the fundamental matrix. Fundamental matrix is a matrix which relates 2 views of different cameras of the same object, of the same scene. So this fundamental matrix can be decomposed into rotation matrix. That's how the camera rotated from one view to another. And the translation vector, which is a shift of the center of the camera. So the camera could shift and rotate. So then after that, I can triangulate these points in the 3D. And I know that these points should fit some cylindrical surface because it's inside the pipe. That's the advantage that I have. And then I can express translation vector in terms of the pipe diameter, which I know a priori. So that solves that problem. And then I can take these images that have been acquired, reproject on the pipe interior surface, and create a mosaic image because all of them are flattened. So it's as if I take the pipe, I cut it along, and then flatten. So that's an example. I just took a bunch of points, random points, spread them on a inner pipe surface, then took 2 views of these points from different positions with different orientation and position of the camera, and that's what I've got. And of course, they look the same. I can match. I can see that this constellation is very similar to that constellation. If you think that this is most likely that, etc. So then I can do the matching, and that's how it happens. For example, these are 3 images that simulated, images that I generated, rendered of this tiger pipe. So then goes this pose recovery process. So I take the set of matched point features, I build the fundamental matrix, then decompose it into rotation matrix and translation vector, and then triangulate point cloud. So this is nothing new about it, and it's it's been developed for many years, and you can find all the details in this Bible of the computer vision. So now I'll show you how the triangulated point cloud looks like once I triangulate it. It's visualized in GeoZooey. So you can see that clearly that the points do lie on the pipe surface. But the problem is that we have these points in a system of the first camera, first view of the camera. And then we have to translate these camera-centric points into pipe sampling points, because after all what we are interested in is how the camera is located inside the pipe. And this is done using the very elegant solution proposed by some Finnish gentleman quite some time ago. So in principle it can be done in a more sophisticated way, more robust, which will take care of possible outliers, mismatches. But I just went along this way because it is simple, clever, and elegant. So how does it happen? So suppose we have points on the in this point cloud. So suppose these are these 3 points which are nearby. So then we can build a normal to this triangle. And we know that this normal should go through the main axis of the pipe. Then we do the same with other 3 points. And again, do the same. And now we know that if we take the vector product of these 2 vectors, we'll get an estimate of the main axis of the pipe. So next step. Now we have to find where exactly this axis, main axis of the pipe, go. And this is done in the next step. So we choose certain point on the axis, and then we build a plane which goes through the this patch on the surface, through the point, projection of this patch on the axis, and some point on the axis. So it doesn't really matter which point is that. So I choose arbitrarily one coordinate, for example, py. I fix it. I just choose it arbitrarily, and then make the system solve for 2 other coordinates. So now I know where the pipe axis goes. And the third step is to find the diameter of the pipe, which is again very simple because I take all the points that I know are lying on the surface. I calculate the distances from these points to the axis and average them all, and I have a reasonable estimate of where the pipe goes. So I need to say that when I take the fundamental matrix and decompose it into the rotation matrix and translation vector, it can be done with a 4-fold ambiguity. So there are actually 2 rotation matrices which satisfy the same solution. And translation vector can be found with up to a sign and a scale. So fortunately, there is a clever Greeks invented a notion of chirality. Very good Greek word. If you want to impress someone, use it, because nobody knows how to spell it. So chirality, in fact, is a very simple thing. All you want is that all the points that you're looking at are in front of both cameras. Obviously, if it would be behind it, how could you possibly see it? So this chirality constraint allows you to remove 3 of the 4 constraints, ambiguities. The 4th ambiguity is the scale, and nothing you can do about it. But fortunately, the pipe radius is known in units of the translation vector. So, and as I know the pipe radius, I can find out the translation vector in real units, because pipe radius is known in real units, in inches or centimeters or miles or whatever. So now I know camera attitude, the position with respect to the pipe, and I can reproject a quiet frame on the cylindrical surface by ray tracing. So that's the result. So these are acquired images, and these are reprojected images. And of course, they look very, very similar. If you may have some trouble finding similar features in these images because they are so distorted. These images are not distorted. There is no problem in combining them in a sensible mosaic. So that's a mosaic that I built. And from 9 frames with arbitrary positions and orientations of the camera. And by the way, this is the seam between one image and the next one. So that's the pore of the same as here. And then the question arises. There is always some error. Because in simulation, no errors. Well, in fact, there are some, and I'll talk about it. But errors are inevitable. So how robust is the procedure with respect to these errors? So I took all the parameters of the camera positions and locations and changed them by 5%. And just so it's a 5% error in every measurement. And then I did the same. The result was bad, which is not bad either. Well, in fact, if you start comparing it with a ground truth, it will be quite different. But do we really care where the crack is in the pipe? Here, or a centimeter away, or an inch away? The fact is that we can see the crack, and we know approximately where is it. So the sources of errors in simulation are 2, actually: rasterization and reprojection. Rasterization is the fact that the image that I've been using for has pixels, and pixels have certain size. And whatever I do, they remain pixels. They are not continuous function. And second, when I do the reprojection, again, it introduces certain errors. But they are not significant, and I expect that in the real situation, and I know that in the real situation there are much more substantial errors than these in my case. But they do not exceed 5% usually with the data I've worked with. So the conclusions. Algorithm works well for simulated images. What did you expect? Otherwise I wouldn't present. So even with some substantial errors, it still produces mosaic which is reasonable and can give the operator some idea about what's inside the pipe. And then of course we need to verify it on the real data, but the data should be collected the way, for me at least, the way I propose, not the way it is done currently. So, thanks. Go to Doosan Babcock Energy Limited in Scotland, who asked if it's possible or not. Also, Gareth Wilson. Also, I would like to thank them for making me sign non-disclosure agreement, which prohibited me from using any data they provided me. Also, I want to thank them for not funding me. Special thanks to Colleen for preparing some pretty sophisticated sketches. Tom is here, Weber? Yeah, right, okay. You were talking about complex images. That's complex images. If you need, go to Colleen. And thanks to everyone who didn't sneak out while during the presentation.
So you can tell us about your experiment, right? The real pipe. You
Well,
just
I
have
have
to show
some-
it to us, so tell us, did it work?
Well, they have data very close to what I found on the web. So it's almost useless. They didn't ever do a calibration of the pipe, of the camera, which is absolutely essential. Most of the time, camera is wide angle, fish eye, because they want to look everything. And these cameras have such strong distortion that it's just very hard to do. Occasionally, when I was restricting to the central part and the camera was moving in the way I wanted it to move, the results were promising. Yes?
I think this is great. I've spent hours in my past life looking at.
Do you want to do that? We'll work together.
Question is that a lot of what you're looking for are cracks. You're not actually ever able to see a point in the inside of the pipe. So
Sure.
how are you picking those points?
Are you sure about that? No, actually, most of the time we look not for the cracks, but for corroded areas. So manufacturing flaws is an important thing, but it's only once when they manufacture the pipe. But what happens when you have a boiler and this steam goes over and over, and then some areas gets corroded, and they don't have cracks, but they have very specific pattern, which is pretty unique. And so there are no problems in detecting special salient points. And also, if there are no salient points, that means that everything's fine with this pipe. We don't need to inspect it, at least here. Yes? Good.
Yuri, is there a way to use the joints between pipe sections
Yes.
for calibration?
Joints, I don't know.
You've got a
Probably
really nice
yes.
weld.
Probably yes. I never never tried to do that. I know that it is pretty simple to extend this Jokinen's procedure to the bending pipe. If you know the radius of the bend, then you can solve, but it won't be a direct solution as in Jokinen's case. It will be iterative solution. But if there are special joints or seams which are expected to be there, they probably could help in determination where the cable is. Yes?
Are there potential applications for medical endoscopy in this type?
Oh, I hope so.
Because there's a bit of a philosophical dilemma. You're assuming that with better ways of imaging through photo mosaics, that you're able to have a better depiction of what this would appear if it was a quickly orthogonal view. Is that correct?
Mm-hmm.
On the other hand, if you have a fisheye lens, all you're trying to do is detect anomalies that they don't necessarily have to be a realistic view.
Yeah, that's right. I think that when someone is doing endoscopy of your heart artery, then they are probably looking for just a single location which they have to clean, and they don't need a complete picture. So, unfortunately, I don't think that all the medical doctors of the world will run to me and will beg me for these techniques. But for the pipes, which is a boring job to watch, and there are so many miles of them, that's probably applicable. Yeah?
You said you had to make an assumption on the scale factor based on the radius of the pipe.
Yes.
So if you intentionally were measuring with a laser or something, that were known separation on the inside, then you wouldn't necessarily have to make that assumption.
Well, I'm not so sure about that. Yeah, if you have probably two laser points, calipers, then it would help. But they have troubles in the putting that they have to put in this head. This head has to have a camera and a light source. So, and you propose to put there lasers? No, I mean lasers? Well, it'll help probably.
Well, I just wonder if that then you'd be restricted to circles, but then you can move to any kind
But
of shape
what-
because you're no longer, you can look at the separation of the laser
Yeah,
and give you
yeah.
some idea
That's-
of orientation.
Yeah, that's true. But on the other hand, just think about it. Imagine that you made a 5% error in this measurement. Then it means that you made a 5% error in length of the motion along the pipe. So you have 5% error in one direction, in another direction. On average, you have, and besides you have an independent measurement of the traveled pipe because of the length of the cable you fed. So I don't think it's a big deal. Yes, Jim?
Could you extend this technique to acoustic imaging? Because I know that Woods Hole ran their Remus vehicle down the New York City water pipe from upstate New York all the way down into the city. They did acoustic imaging. But New York wouldn't release the images, but I was curious if this technique you could use to help find anomalies in the pipe.
Don't know. Yeah, I never thought about that. Acoustic is different from vision.
I worked on that project. So they took pictures in the pipe. So is that what you meant by acoustic images? Like underwater pictures? Yeah. So they took pictures of it, but the problem was there were 13 cameras around, not just
They had
one.
acoustic stuff too, but there was some.
So there was the hydrophones were to track it. The acoustics was to track it. They didn't
At
go
one point
back.
they were talking about using
No.
acoustics for.
So was it a ranging
It was
cameras?
But
Ranging camera. So they were measuring range.
no, they were just taking pictures. They were looking for
Oh.
cracks.
So it was actually a visual
Yeah,
application.
visual. And then I sort of, there were a few of us who were low pay grade, would go through.
I know
Thousands
they're
of
working
images.
on seeing if they can do it acoustically. but I
Yeah,
guess
when I left, they
didn't
were-
get it.
They were working.
It would be interesting because the thing is if you
Yeah.
wanted to run down an oil pipe with oil in it or something,
Well,
then you
yeah.
could use acoustics where optics may be a problem.
That was going to be my next question for you is in that situation where you have multiple cameras around the diameter, I mean, we're talking 13, 15-foot diameter pipes. So you're not just talking one camera in the middle. Could you do that sort of mosaicing?
Yeah, certainly can, but there is no need probably. I would rather go for a crawler, which does perfect job without any need for mosaicing. So it just turns the head and then makes the stripes. It does the job perfectly well. But this is only for the case when a crawler cannot fit
Yeah.
into the pipe.
You can't get, in the New York City tunnels, you can't get the crawlers in because the shafts are too.
Cut the
There's no
the
water in New
crawler
York
in.
City.
Off it goes.
Thanks, Yuri.
This time.
Why did we both? What? Yeah.
I know,